Thank you very much. So maybe we should start by correcting some references that were controversial yesterday. So as was pointed by Sasha and Slava, so in 1940, von Neumann gave an account of his theory of invariant means and invariant measures, and that was actually reissued by the American Mathematical Society a few years ago. So it's highly recommended. But in fact, he proved the existence of an invariant measure on a compact group in 1933. And he considered amenable groups already in 1929, as was pointed out. And indeed, the existence of invariant measure on compact spaces was proved by Krylov and Boglyubov already in 1937, at least, or maybe earlier. So, so I apologize for these inaccuracies. I hope there won't be any more typos, but probably there will. So what I would like to do now is to describe the plan for the next three talks. The first talk discussed averaging operators in dynamical systems. And we also formulated some effective ergodic theorems. Today, we're going to talk about unitary representations, operator norm estimates, and counting lattice points. Tomorrow, I would like to talk about best possible spectral estimates, the automorphic representation of a lattice subgroup, and the duality principle on homogeneous spaces. Of course, all of these terms will be defined and explained in some examples. And finally, on the last talk, I would like to describe some what I believe are interesting applications of spectral theory to questions in ergodic theory proper. So we will discuss fast equidistribution of dense lattice orbits and best possible Diophantine approximation on homogeneous algebraic varieties. Okay, so just as a reminder, we discussed the averaging operators associated with an ergodic action. More generally, let's consider averaging operators in general unitary representations. So let G be a locally compact second countable unimodular group with Haar measure Mg. Bt is a family of sets of finite measure with measure going to infinity. And pi from G to the unitary group of a Hilbert space be a strongly continuous unitary representation of G. That is to say, a continuous homomorphism G to the unitary group of a Hilbert space H pi with a strong topology. And now for the Haar uniform averages beta t supported on Bt, we define the averaging operators pi x beta t. It's a bounded operator acting from age to age, given by pi beta t of a vector v, is the average of the translates. Here it is. We translate v by g, ranging over the set bt. So this is a convex average of isometric translations of the vector v. And we would like to study their norm convergence properties, ideally establishing operator norm decay estimates. This is a possibility that came up yesterday. That's what we would like to realize, including for the representations of the form pi x naught on L2 naught for an ergodic probability measure preserving G action on X. And I remind you that all of our actions really are going to be ergodic, and the naught in L2 naught denotes the space of zero mean functions, the space of functions orthogonal to the constants. So a very useful operator norm estimate is associated with the notion of weak containment. So let pi and sigma be unitary representation of an LCSC group G, and assume that sigma is isomorphic to a subrepresentation of pi. In that case, it's totally obvious that for every probability measure beta on G, the norm of the operator sigma beta is less than or equal than the norm of the operator pi beta, because you simply look on a subspace. Okay, that's for a subrepresentation, but actually this inequality holds whenever diagonal matrix coefficients, namely functions of the form sigma g VV that came up in Michael Cowling's talk. So whenever diagonal matrix coefficients of sigma can be approximated uniformly on compact sets in G by convex combination of diagonal matrix coefficients pi g w product w of pi. And the latter condition is called weak containment, and it's denoted by sigma weakly contained in pi. This condition is definitely weaker than being an actual subrepresentation. Sorry? Yes. Yeah, that's, yeah. Unit vectors in their respective Hilbert spaces, and we approximate one matrix coefficient, in this case positive definite function, by a convex combination of those from a different representation. So this condition is called weak containment, and the reason we're interested in it is that it was established in Diximier in 1969 that weak containment is equivalent to the norm inequality. The norm of the operator sigma f is less than or equal to pi of f for every f in L1b. I'm sorry, in L1g. Okay, so we are going to be mostly interested in norm inequalities. And so we deduce from this analysis, I'm not exactly sure who defined weak containment, maybe it was Fell, but this property was established by Diximier, and so weak containment is enough for us to deduce a norm inequality. So, for example, of a few things we basically already seen, the existence of an asymptotically invariant sequence in G is equivalent to 1G being weakly contained in RG, namely to the trivial representation of G being weakly contained in the regular representation. That's just, well, I mean, one direction of it is an exercise in the definitions. And so it's also quite clear that this condition is equivalent to the norm of RG beta being equal to 1 for every probability measure beta. And this condition characterizes amenable groups, actually. This is called Reiter's criterion. Just to tie it with a few of the things we discussed yesterday. And property T is characterized by the trivial representation being separated from unitary representations without invariant unit vectors. And equivalently, it's characterized by the fact that the supremum over all such representations pi of the operator norm pi beta is bounded by a certain number, alpha of beta, which is strictly less than 1 for every generating measure beta. So this is a very, very strong uniform estimate which characterizes property T. So given what we have said here in Reiter's criterion, essentially, we can see that non-amenable groups are characterized by the fact that there exists measures beta such that the norm of RG beta is strictly less than 1 in L2G. If it's always 1, then the group is amenable. Okay. Equivalently, the averaging process associated with a random walk on G defined by the convolution operator Rg beta f equals f convolved with beta, this averaging process for f in L to G is contractive. Namely, the averaging process has norm less than 1. And we will call a unitary representation pi of G a tempered representation if pi is weakly contained in the regular representation. And then it follows that the norm of pi beta is less than or equal than Rg beta for all absolutely continuous probability measures beta on G. Maybe I should stop here to say that this inequality that we have right here is going to be very, very significant for us, because the reality of it is that if you have a complicated group and this group has a very complicated set of representations, then it's essentially an unfeasible task to say anything about the norm of pi beta. On the other hand, the norm of a convolution operator on the specific space L2G, if you're very lucky, is something which can be analyzed and estimated. And I should also say that the convolution action, or the right or left regular representation, they can be described geometrically. One can use various estimates and various kernel estimates, and you could imagine that it's going to be possible to estimate the norm of a convolution operator in the regular representation. And whenever you have some alternative argument which says that your representation is tempered in a suitable sense, or, well, some version of it is tempered, then you will deduce this norm inequality. And this norm inequality, given what we have in the first line, is going to be very significant, because the norms of convolution operators on non-amenable groups are usually of norm strictly less than 1. Okay, so it is okay, so this is just what we said. And so the main point of what we are going to do, or the main, say, realm where these kinds of arguments are going to be successful, is for an extensive class of group which consists of non-amenable algebraic groups. Because there it is actually possible to establish operator norm estimates which go far beyond the contraction property guaranteed by a spectral gap. And in these norm estimates, the regular representation plays a major role. So I remind you from yesterday that while this inequality is very nice, it is highly unsatisfactory for us. We will have, in dynamics, there's going to be very little you can do with this inequality. What you really have to insist on is that as you take a collection of sets BT, then this norm will actually decay. There's no dynamics without taking a collection of sets which are growing in G. And you're going to have to show that this collection has, let's say, I mean, this would be a good conclusion, has norm decay. Okay, so we are going to discuss very, very briefly some elements in the representation theory of simple algebraic groups. This is going to be very closely connected to the content of the talk of Michael Cowling yesterday. And the first thing we would like to define is the notion of integrability of matrix coefficients, which is a measure of decay, as we shall see. So a unitary representation pi of G on a Hilbert space is called an LQ representation if there exists a dense subspace H pi prime contained in H pi such that the matrix coefficients given by CVWG is the inner product of pi g v and w are in LQG for VW in this dense subspace. And we can define the integrability exponent of pi to be p plus pi equals the infimum of such q where pi is an LQ representation. And since for unit vectors v and w we clearly have that the matrix coefficient is bounded by 1 because pi g is a unitary operator, it follows that if that pi is LQ integrable for an open, well, at least for the open interval q strictly larger than p plus pi. Namely, if you take a higher power of the function, then it's going to decay even faster. Okay. And another side remark is that, which will be useful a little bit later, is that if pi is an LQ representation and sigma is an LS representation, then h pi prime tensor h sigma prime is dense in h pi tensor h sigma, where h sigma prime is the dense subspace of h sigma, etc. And pi tensor sigma is an LR representation with the usual exponent relation, which is 1 over r equals 1 over q plus 1 over s. So, for example, if q equals s, then pi tensor sigma is already an LQ over 2 representation. You need to take a lower power in order to make the matrix coefficients converge. And so let's consider unitary representation of simple algebraic group, and let sigma be irreducible, infinite dimensional unitary representation of such an LCSC simple algebraic group. And then p plus sigma is strictly less than infinity. In other words, sigma has a dense set of matrix coefficients which belongs to LQG for all q greater than p plus sigma. This is a truly remarkable fact. It's the culmination of a very long series of works which starts perhaps with Harishchandra, and other major contributors were Cowling, Howe, Moore, Borel-Wallach, and there are, this has become a very elaborate theory, and there are many contributors later than that. It's a very simple statement in the end. The bottom line statement is very simple, but there is a very significant amount of work that goes into this result. So I'm not going to try to explain it. This is not a realistic thing within such a short time, but I do want to emphasize it, and I certainly want to explain how one uses this remarkable, ultimately remarkable spectral estimate. Furthermore, G has property T if and only if P plus sigma is less than or equal than some fixed constant P of G, which is strictly less than infinity, uniformly for all such sigma. And this goes under the name of quantitative property T. That's a very common notation for this, appellation for this fact, which was also considered by these authors, which was also established by these authors. And now we come to a very important point, which is that if n, if the integer n, is strictly greater than p plus sigma over 2, then the representation sigma tensor n has a dense subspace of matrix coefficients which are in L2G. This is a very simple fact. If you think about the tensor product argument that I just mentioned, it simply means that if you look at matrix coefficients which are product of the constituent matrix coefficients, it suffices to take it to this power in order to land in L2G. So it follows from that that sigma tensor n, the unitary representation sigma tensor n, is isomorphic to a subrepresentation of a multiple of the regular representation. And this analysis has been carried out by Cowling and Howe and Moore. And a somewhat sharper result, as far as we are concerned, is that if n is greater or equal to p plus sigma over 2, then sigma tensor n has a dense subspace of matrix coefficients in L2 plus epsilon g for every epsilon. But perhaps they're not in L2, which is definitely a possibility. And then sigma tensor n, the unitary representation sigma tensor n, is weakly contained in the regular representation. The conclusion there that it's actually isomorphic to a subrepresentation is on the face of it stronger, and it is stronger, but in terms of what we are really after, which is an operator norm estimate, this result is good enough for us, as we shall see. And this result was established by Cowling, Hagerup, and Howe. So now, this is already a good start, because we start from a very, for those of you who are familiar with how complicated the representation theory of let's say, a simple Lie group such as SL3R is, this is a very comforting beginning, because it shows that the most general representation, and this is really a very complicated object, what you're going to have to do, you're going to have to take a tensor power of it, but then you will be able to compare it to the regular representation, which is one fixed, nice geometric representation. Okay, so what do you do in the regular representation? And so we would like to develop operator norm estimates in the regular representation. And for that, we are going to make a note of the fact that convolution operators on simple algebraic groups obey a remarkable inequality known as the Cosy-Star phenomenon. And the Cosy-Star phenomenon says the following. It says that for every function in LSG, where S is strictly less than 2, we have for every f in L2G that the L2 norm of the convolution f, capital F convolved with f, is bounded by a fixed constant times the LS norm of capital F times the L2 norm of little f. Okay. Why are we interested in this? Because you see that the L2 norm of G appears on both sides of the equation. So this equation tells you that the norm of the convolution operator, which is defined by capital F, is bounded by a constant time the LS norm of the function capital F. Okay, so so we'll see in a minute how we're going to exploit this. So this is the so-called Kunzi-Stein, this is the Kunzi-Stein convolution inequality, but I want to emphasize it as giving an operator norm bound on convolution operators. Okay, and this inequality was established by for SL2R by Kunzi and Stein in 1960. And they also established the result for all simple Lie groups when F is bi-K invariant. K, a maximal compact subgroup. I'm mentioning this because this is really a radically simpler proof than the general case. And sometimes bi-K invariant sets are enough, but not always. The general case was established by Cowling in 1978 for simple Lie groups using Hertz's majorization principle to reduce the problem to that of estimating the operator norm in the boundary representation. And for simple algebraic Chevalley groups over local fields, the inequality is due to Vecca using the same method. So I'm not going to get into the proof of that. The proof of the general Kunzi-Stein phenomenon is really very demanding. And there's a lot of complicated analytic ingredients that and also elements of the structure theory of simple groups. It's really a handful. I could have presented the result for bi-K invariant averages, but I've decided not to. Anyway, it's of course a well-known and very well-established result, and now we can formulate the following statement, which we're going to call the spectral transfer principle. But before that, let's consider the following corollary. We can consider every probability measure on G of the form beta, which is the characteristic function normalized by its measure. These are definitely functions on G, and these functions on G are, of course, in every LS. This is just the characteristic function of a bounded set. It's not an issue. And then the Kunzi-Stein phenomenon says that for all S between strictly less than 2, the norm of RG beta is a convolution operator, which we've discussed several times. The norm of this convolution operator is bounded by the LS norm of the function chi bt divided by its measure. So all we have to do is integrate over bt of the function 1 and take it to the power 1 over s and divide by the measure. And what we get is this very uniform and general operator norm decay. This norm of the convolution operator decays like a power of the measure. And I'm already going to emphasize it here that the generality of the Kunzi-Stein phenomenon is such that I can take literally every bounded set in G, because it's a convolution theorem in Lebesgue spaces. Okay, so the LQ property of irreducible unitary representations can be combined with the Kunzi-Stein phenomenon and Jensen's inequality to give the following remarkably general operator norm estimate for probability measures on simple algebraic groups, which we like to call the spectral transfer principle. It says that for every unitary representation pi of G with a spectral gap and no finite dimensional invariant subspaces, and for every family of probability measures, beta t given as normalized Haar measure on a set, the following norm decay estimates holds for every epsilon positive. The norm of the operator pi beta t is bounded by the norm of the corresponding convolution operator to some root 1 over ne pi. And because we already have this inequality, we can state this as it's bounded by C epsilon times m bt to minus 1 over 2 ne pi. And here, ne pi is the least even integer which is greater or equal than p plus pi. So let me go back for a moment. P plus pi is the integrability exponent of the representation pi. Every representation pi has an integrability exponent in our setup. Ne pi is the least integer greater from it. We are going to take the tensor power n pi to the power ne pi, and then we can apply the statement that the tensor power is weakly contained in the regular representation. And then we have this norm inequality. So in a completely general representation with a spectral gap, we conclude that we have a rate of decay for the operator norm which is given by the measure of the set to some negative power. Okay. And so from this, it's not going to be a long way to the effective mean ergodic theorem. It's an immediate consequence. So in particular, we can bound the norm of the averaging operators of pi x beta t acting on L2 naught when the action is ergodic and weak mixing, namely has no finite dimensional invariant subspaces. We simply consider the representation pi x naught. So we have the following effective mean ergodic theorem. For any weak mixing action of a simple algebraic group G which has a spectral gap, and for any family Bt in G with, whose norm goes to infinity, the convergence of the time averages pi x beta t to the space average takes place at a definite rate. Pi x beta t f minus the integral of f on x in L2 x decays like a negative power of the volume. So for those of you who are familiar with the ergodic theorem, for example, for RD or for ZD, I would like to point out that the only requirement needed to obtain the effective mean ergodic theorem is simply that the measure goes to infinity. And the geometry of the sets Bt is not relevant at all. The sets Bt don't have to be connected or open or defined by a metric or defined by a norm, and they can move, so to speak, in different directions in G. The only thing that matters is that they have growth. And under this condition alone, this is sufficient to get the mean ergodic theorem. So in some sense, and in fact the effective mean ergodic theorem. So in some sense, this is an ergodic theorem which is far, far better than the abelian or amenable case. And once again, the reason for that is that every representation, every irreducible representation of our collection of groups has a certain LP matrix coefficients. And because of that, it has a tensor power in the regular representation, weakly or strongly. And once you are comparable to the regular representation, you can deduce from the Cosy-Stein inequality that the norm of this general operator, pi beta t, is bounded by some power of the convolution norm of the same measure. And I should say by Cosy-Stein, it then follows that you have norm decay as a certain negative power of the volume. So that's the gist of this result. And I would like to emphasize that this fact allows a great deal of flexibility in the application of the ergodic theorem. I mean, I generally think that this is a fact which is not fully, I would say, realized. There are a number of directions in which one can take it. Okay, so we have our operator norm decay estimate. So what are we going to do with it? Okay, so essentially the rest, yes?
Excuse me, Amos. I'm confused because at a certain point you defined this integrability exponent only for irreducible representation. Now you are talking of some unitary representation.
Yes, there's a certain...
The result of Marcus yesterday?
No, I'm not using his result of yesterday. I'm using his results of 30 years ago. There's a certain amount of analysis of direct integrals that goes into it. Well, in principle, you see, if a fixed tensor power of every irreducible representation is in the regular, then that would be also true for a fixed tensor power of a direct integral. So, because it'll be just a sum of representation. Let's say, roughly speaking, it'll be a direct integral of representations weakly contained or strongly contained in the regular. But certainly, I mean, the honest answer may be is that I'm skipping a number of things here. There's a certain amount of analysis that has to be performed, but that has really been done by Howe Moore paper, for example, another paper of Howe on symplectic groups, Cowling's paper. Yeah. Okay, so let's make some comments on the spectral transfer principle. So the norm estimate of the operator pi beta in a general representation has been reduced to a norm estimate for the convolution operator Rg beta in the regular representation. So this establishes for simple groups an analog of the transference principle for amenable groups that made a very short appearance yesterday. But I think it's interesting because philosophically it's really quite similar, that you can, reduce maybe is a strong word, but you can estimate the general representation of a simple group by the regular representation if you're willing to take a tensor power. And when the sets are bi-K invariant for a suitable maximal compact subgroup, a better estimate holds, namely, well, it's an estimate of a very similar nature, but it allows for a somewhat faster decay. Maybe this is not a point we should dwell on. Yeah, I mean, there are a number of, one can make these things very explicit and quantitative. And now what we would like to do is turn to our first application of the effective mean ergodic theorem for averages on simple algebraic groups. And that would be the solution of the lattice point counting problem in domains Bt in G. Okay, so let G be an LCSC group and gamma in G a discrete lattice subgroup. And that means that gamma is a closed countable subgroup such that G mod gamma has G invariant probability measure. And, well, I mean, it's quite an elaborate theory, so I will just mention that, of course, yes?
I just have a question. In your estimates, where does the fact that you have spectral gap in your coefficients? I don't see in your theta or something, but
Well, without the spectral gap, it is definitely not true that you have a finite n such that the tensor power is contained in the regular. Yes. Certainly, for example, SL2R has ergodic measure-preserving actions on a probability space which do not satisfy this property and do not have a spectral gap. Okay, so for example, the model that everybody has in mind to a certain, well, initially, is the lattice, I don't know, ZD in RD. We also mentioned the lattices SLNZ inside SLNR and maybe fundamental groups of closed finite volume, of finite volume hyperbolic manifolds, etc. But we are going to keep the discussion rather general, actually, and keep our LCSC group G. Now, the lattice point counting problem in domains BT and G calls for obtaining an asymptotic for the number of lattice points of gamma in BT. So we simply look at the intersection of gamma in BT. BT is bounded. Gamma is discrete. There's only finitely many points like that. And we would like to count how many. And ideally, we would like that Haar measure would be the main term in the asymptotics. The first guess of how many lattice points you have in a set B is the volume of B. If you think maybe on ZD and RD, you will find this probably very plausible. And we would like an error estimate of the form gamma intersect BT divided by MBT, which is the main term, should be 1 plus an error term which decays like a negative power of the volume, where delta is positive and is as large as possible and hopefully given in an explicit form. Here, I'm using the fact that I've normalized G mod gamma to have a probability measure, okay? And so this is the two principal terms in an asymptotic, a main term and an error term. And we would like the solution, that the solution applies to general family of sets BT in a general family of groups. And that is to allow for a wide variety of counting problems which arise in applications. And this is really not just a nicety. It is, in fact, the case that many natural problems call for counting lattice points in fairly strange sets. That is true, of course, even in the abelian situation, and the flexibility in what sets you can count lattice points is really quite significant. And finally, we would like that the solution should establish whether the error estimate that we had before can be taken as uniform over all, or perhaps some, finite index subgroups lambda in gamma. Of course, a finite index subgroup is a lattice in its own right. And we could count the points of that lattice too. But if it's a finite index subgroups, what we would really like is that the solution is going to be uniform over, I don't know, maybe all finite index subgroups and their cosets, so that if you have such a group lambda, then the intersection of gamma lambda with BT divided by the volume is going to be given by the index plus an error estimate which decays at the same speed. In other words, there's no loss in the error term. That's the meaning of uniformity. Now, this may look like a strange property, and here, of course, we'd like delta and the implied constant to be independent of the finite index subgroup and the coset representative. This may look like a somewhat strange requirement, but if we go back to the example of SLNZ, Well, SLNZ has a very natural collection of finite index subgroups, which are so-called congruent subgroups, which are, say, all the matrices in SLNZ congruent to the identity modulo P. And there are a number of very nice applications where one would like a uniform estimate for all congruent subgroups for very good reasons. So the main point of our discussion of the lattice point is that a general solution obeying these four requirements can be given for lattices in simple algebraic groups and general domains. And the method is based on the effective mean ergodic theorem for G. Okay, so now I would like to present, so one of the things I would like to emphasize is that the solution of the lattice point counting problem, given the effective mean ergodic theorem, is really quite straightforward. And I would like to take the chance and present a proof of it, which is essentially, I would say, complete. So this may, okay, so we'll see how that goes. The first thing we have to say is that some stability and regularity assumptions on the set BT are necessary for the lattice point counting problem. This is absolutely obvious. There are only countably many lattice points. So you can throw this countable set and that's it. So there's no question that if you want to identify lattice points in certain sets BT, then they're going to have to be nice sets. That's true, of course, in ZD as well, ZD and RD as well. So assume G is a simple Lie group and fix any left invariant Riemannian metric on G. And let O epsilon be the set of G in G such that the distance from G to the identity is less than epsilon. With your permission, I'm going to stick with simple Lie groups, or, well, connected Lie groups. Although the result is much more general, but this would be a more streamlined presentation. All the main ideas are really here. So an increasing family of bounded Borel sets BT of G will be called admissible if there exists a constant C such that for all t greater than some t naught and all epsilon smaller than some epsilon naught, we have two conditions. We have stability and volume regularity. Stability means that if you take the set BT and you perturb it on the right and on the left by a small neighborhood, then you're still going to stay in your family, but you have to increase the parameter only a little bit.
So maybe there exists C, epsilon 0, T0.
Sorry?
Maybe there exists C together with T0.
Yes, yes.
Epsilon 0.
Yes, yes. Yeah. Thank you. Now, of course, you see that already this condition says that BT plus C epsilon contains a very large open set, right? Because you take BT and you make it open. Okay. So obviously these sets are very constrained, or, well, relatively constrained. Now, this condition is actually very natural and sort of mild. All it says is that the log of the measure is a Lipschitz function. So, okay, that's another condition. And we will call such sets admissible. Admissible sets are not the only ones for which the lattice point counting problem is going to hold, but it's the easiest case to handle. Maybe I should say just very, very briefly that when BT are admissible, pointwise almost sure convergence holds for the averages beta t with a prescribed rate of convergence. I'm just going to say this in one line. We discussed the mean ergodic theorem. The mean ergodic theorem is very general. We are not able to prove the pointwise theorem in the same generality, and presumably it's not true, But if the sets are admissible, then the mean ergodic theorem can be elevated to a pointwise, almost sure convergence with a similar rate. But let's stick with our admissible sets. Okay, so let G be a connected Lie group, and gamma a lattice, and BT are admissible. And now assume that the mean ergodic theorem holds for beta t in the ergodic probability space L2 of G mod gamma. Namely, pi beta t f minus the integral of f over G mod gamma converges to 0. Then the conclusion is that the number of lattice points in BT is asymptotic to the volume. This is a preliminary result. And the result we're after, so here we only assumed the mean ergodic theorem, okay? And what we got is the main term. And now assume that the error term in the mean, or the rate, maybe I should say, in the mean ergodic theorem for beta t in L2 G mod gamma satisfies this norm, this operator norm decay. And because that's what we anticipate, it satisfies the norm decay as a negative power of the volume. Then the number of lattice points in the intersection divided by the main term, divided by the volume, is 1 up to a certain error estimate, and the error estimate is compromised in relation to the mean ergodic theorem. Here we had minus theta, and here we have minus theta over dim G plus 1. Okay, so how much time do I have left?
10, 15?
Sorry?
10 or 15 minutes.
Ah, okay, very good. So, so there is a drop in the quality when one goes from the effective theorem to the lattice point counting problem. This is a very fundamental issue, and we're going to go, perhaps we're going to go back to this in a little while. Okay, so let's try to prove this theorem. And so the first thing we have to explain is, how does one apply the mean ergodic theorem? Well, let's take O epsilon to be a small neighborhood of the identity, and let's take chi epsilon to be the characteristic function of O epsilon divided by its measure. So we normalize, it's a normalized bump function, well, normalized characteristic function. And then we can consider the gamma periodization of this normalized characteristic function. We simply sum its translates under gamma. We sum its right translates under gamma. That makes it into a gamma invariant function. It's well defined because it has compact support. And so we have a little function which we have projected to G mod gamma. Okay. And so phi is a phi, or phi epsilon, is a bounded function on G mod gamma with compact support, whose integral over G is 1. And so the integral over chi epsilon over G is 1. So the integral of phi epsilon over G mod gamma is also 1. Okay, now let's apply the mean ergodic theorem to the function phi epsilon. And of course, it follows from Chebyshev's inequality that if you look at the set in our probability space where the average deviates from the mean by more than delta, then this measure is going to go to 0. Okay? Because of the content of the mean ergodic theorem. And so in that case, in particular, if this measure of the deviation set is going to go to 0, for sufficiently large t, the measure of the deviation set is going to be smaller than the measure of O epsilon, which is some fixed number. And so there's going to exist a point gt in O epsilon which is outside the deviation set. So that pi g mod gamma beta t acting on phi epsilon at the point gt minus 1 is less than delta. Gt gamma is not in the deviation set. And we conclude that given epsilon and delta, for t sufficiently large, there exists some gt in this small set, O epsilon, such that the average that we have, this is precisely what we have here. It's just that I've taken the one outside. Yeah, it's exactly the same equation. So this average of the translates of phi epsilon at the point gt by points g in bt is between 1 plus delta and 1 minus delta. So this is a completely elementary conclusion of Chebyshev's inequality. Now, as it turns out, we are talking about averages on G here, and we will be able to interpret them geometrically. I mean, what do we do after all? We take, okay, so let's continue. So on the other hand, by definition of phi epsilon and the averaging operators, pi g of gamma beta t phi epsilon, by definition, is this average. And phi epsilon is a certain sum. That was the definition of phi epsilon. It's the periodization. It's the periodization of chi epsilon, right? So I can write this by changing the order of summation as the sum over gamma. The sum over gamma of 1 over mgbt, and here we have an average of the function chi epsilon on G, averaging its translates under bt. So practically speaking, what we have is a little bump function, chi epsilon, which we move basically by gamma and G, and G or G inverse. And we would like to understand where does this function actually live. So what do we mean by that? We have the following basic comparison argument. We claim that if we look at our expression, this expression over here, then this expression, the integral over bt minus c epsilon of phi epsilon is less than or equal than the number of points in gamma intersect bt, and less than or equal to the integral over bt plus c epsilon of the same expression. And this is a completely elementary consequence of admissibility, as we now see. So supposing that you wanted to estimate the left-hand side, and remember that the left-hand side is an infinite sum, well, actually a finite sum of gamma translates. So suppose that chi epsilon G inverse of chi epsilon of G inverse H gamma is non-zero for some G in this set. And some H in O epsilon. Then if you write the condition of G inverse H gamma belonging to the support of chi epsilon, namely belonging to O epsilon, you will come up with a condition that gamma is in H inverse bt minus c epsilon times the support of chi epsilon. And under this condition, this set is O epsilon times B, contained in B, O epsilon times BT minus C epsilon times O epsilon, and by admissibility it contains in this set. That was the condition of almost of stability. So that means that if you are to estimate this expression, right, then you're going to have to sum over all of gamma. But really, this is not going to give you anything non-zero unless gamma is in BT. Okay, so that means that you have so you have this inequality that this integral is bounded by the sum over gamma in BT, the integral over BT of chi epsilon, and of course the integral of chi epsilon is bounded by 1, so we have at most gamma t many elements times 1. So this is one comparison argument. The other comparison argument is very similar. So maybe I should skip this. You can do exactly the same thing on the other side. And so if we take t sufficiently large and we take age in GT, which we took the precaution to take in O epsilon, if you remember, then using claims 1 and 2, we can deduce the upper estimate, for example, that gamma t is bounded by 1 over delta times the measure of bt plus epsilon, and once again by admissibility, it's bounded by 1 plus delta, 1 plus c epsilon over times mbt. And so the lower estimate is similar. And if you look at this equation, then you see that if you divide by bt, then we have an upper bound for the number of lattice points, and we have a lower bound for the number of lattice points. And so we got the main term. Yes. Okay, so I haven't explained how to do the error estimate, so I think that we're going to take 2 or 3 minutes tomorrow and do that. And I will also then explain a little bit about the history of the problem and mention some of the previous work. So thank you very much for your attention.